What's going on, everyone? Today's objective, I could find any term in an arithmetic sequence. So we spoke about recursive formulas already. Now we're going to go into what we call explicit formulas. The big difference with recursive formulas, in order to know the next term, you must know the previous term. With explicit formulas, you don't need to. You could find any term at any time. So explicit formulas are used to find the nth term, or we'll call it any term, in a sequence. So we'll use the bottom example, and we'll notice some similarities in this example and things that we've seen before. So let's say I'm going to say let a sub n equal 2n plus 5. If n is equal to 7, then, and let's find the seventh term. But let's take a look at this first. So we've actually dealt with explicit formulas before. This should look like a linear equation that has a slope of 2 and a y-intercept of 5. So this is actually an equation in slope-intercept form. A sub n is equal to 2 times n plus 5. We might see it as y is equal to 2x plus 5. So we've seen explicit formulas already. So we want to do this, and we want to find what looks like to be the seventh term. Okay, well, if I want to find the seventh term, all I would do is I would take that 7 and substitute it in for n. And then we ask ourselves, what's 2 times 7 plus 5? Well, 2 times 7 is 14, plus 5 is 19. So using the explicit formula that we were given, we could find any term. Explicit formula shown here. All right, a sub n is equal to a sub 1 plus n minus 1 times d. All right, we already know a sub 1 means the first term of the sequence. The letter n represents our term number, and the letter d represents our common difference. So this is the explicit formula for an arithmetic sequence. All right, so we're going to try to kind of rewrite this formula given specific sequences. All right, so finding the nth term of a sequence, and I'll leave this little explicit formula up here to help us out. So if we're given the sequence 81, 85, 89, 93, 97, we want to find the 23rd term. Now we can count on our fingers and toes until we eventually get to that 23rd term. I think it would be easier if we just use the explicit formula. All right, so let's use exactly that. All right, so a sub n, I won't say a sub n, I'll say a sub 23, meaning our 23rd term, is equal to, well, what's my first term? My first term is 81 plus n minus 1. So what do we say n was? N is the term number, and the term number we're looking for here is 23 minus 1 times what is our common difference? Well, what is our common difference? To go from 81 to 85 to 89, looks like I'm adding 4. So our common difference is going to be times 4. And let's find it. Let's find our 23rd term. So a sub 23 is equal to 81 plus 22 times 4. Okay, so a sub 23 is equal to 81 plus 88. Therefore, a sub 23 is equal to 169. So what is our 23rd term? Our 23rd term is 169. All right, let's use the same thing. Let's use the same formula. Given the sequence 47, 39, 31, 23, 15, let's find the 102nd term. All right, let's do it. So a sub 102 is equal to, so let's actually write that a little bit smaller. A sub 102, make my a not look like a 9, A sub 102 is equal to our first term. So our first term here is 47 plus n minus 1, so 47, I'm sorry, not 47, 102 minus 1 times what is our common difference? Well, it looks like my values are decreasing, so I have a negative common difference. And it looks like it is decreasing by 8. So times negative 8. Remember, I'm not subtracting. Over here, I'm not subtracting. I am multiplying it by my common difference. So times negative 8. Okay, so that means that a sub 102 is equal to 47 plus 101 times negative 8. All right. So a sub 102 is equal to 47. Let's do, should be what, 808? Let's find out for sure. Not trusting my mind right now. 101 times 8. Yep, 808. Okay. Minus 808. And we will finish it off there. Therefore, a sub 102, meaning the 102nd term, will be 47 minus 808, which is negative 761. So there you have it, using explicit formulas to find terms.